Homework 41, page 614, we're just moving into the next section. So chapter 10, section 2, 1 through 13 odd, and 19 through 23 odd. Okay, most differential equations aren't solvable in the sense that you get an explicit formula for a function. So what's a solution to a differential equation is a function. And most differential equations, you can't get an explicit formula for that function. But there are workarounds to that. This is one of those workarounds. So what we're going to talk about today is one of those workarounds. In many cases, if you have a differential equation, let's say y prime plus y squared equals, did I say x squared? In many cases, what you could do is if you could isolate the derivative by itself, get it by itself, which we can in this case, y prime equals x squared minus y squared. Okay, so now it's understood here that y is a function of x. We could also have written this as dy dx plus y squared equals x squared. It all means the same thing. But here, if all you see is a prime, if there were no x there, then you could call the input variable whatever you want. But in this case, since there's a y with a prime on it and an x, well, we're just going to assume that what they mean by that is that x is the input. Okay, so, okay, in this case, we could actually, we could do something with this. And I've alluded to this, or actually, we actually worked one out last time. We're going to create what we call a slope field. Because what this is, we're imagining there is some function, y of x, and we want to know what is it, because that's the solution to this differential equation. And we want to be able to approximate this thing. And so what we're going to imagine is that we have a formula for the slope at any given point on the plane xy. You give me 3, 2. I want to know, okay, what does that thing look, what does the function look like there? And I could say, well, y prime is equal to 3 squared minus 2 squared there. That's what the derivative there looks like. And so that's the same thing as 9 minus 4, so that's 5. So the function right there, nearby, in a neighborhood of 3, 2, would look like a line that has a slope of 5. That's what it would look like right there. I could do that with any point on the plane. I could say, what about -1, comma, let's say 2? Well, let's see. Y prime would be -1 squared minus 2 squared. So the derivative there, the function would look like 1 minus 4 is -3. So if I zoomed in right there, what that function would look like is a negative slope of -3 right there. Right? Yeah. This is all making sense? Yeah. Okay, so then what we can do is do that with the entire plane. The problem is we don't have time to do all the infinitely many points on the plane. So we have to choose how many points we want to work with. But to get a general idea, well, and it's going to depend on the differential equation itself. And where you care about your points being, right? So like, for instance, if this describes, if we had some differential equation, y prime equals 2t, we're thinking about this thing as being a function of time, maybe we don't care about negative times. So why would I care about negative values of t? And if I understand that my thing is, like population, for instance, we didn't care about anything below here because you can't have negative populations, right? Yeah. So it's going to depend on your setup. But in general here, we could just say, well, usually I'm going to split the x, or I'm going to want to get a picture of what happens, you know, in some area where the origin is at the center of it. If I just want, if without any more information than this, I'm just going to take this.
Yeah.
Okay? And so what I'm going to do, one way of doing this to kind of figure out what is it doing here is to make a table of all of these values. And so I'm going to make a table here. I'm going to put my y's over here, my x's over here, and I'm just going to say, I don't know, maybe y starts up at 2, 1, 0, negative 1, negative 2. Notice the order I did that in. Because what I'm gonna do, I know what I'm going to do. I'm gonna construct a slope field, right? I'm gonna have a bunch of different points, and I want to know what are the slopes at those points, like this. And so the way I lay out my table is so that I'll be able to look here and go, ah, it's that one. Does that make sense?
Yeah.
Ditto with x. I know x goes from, and I'm going to say, I guess, negative 2 up to 2. So negative 2, negative 1, 0, 1, 2, and you can see what we're gonna get from that. All right, so now we have our table, and basically I've just said, all right, we take these. What is this? 25 points. 5 times 5 is 25 points. I just want to know what's going on at these 25 points here, right? And so what I'm going to do is just compute. It tells me how to compute the slope there, right? I plug in a 2 for x and a 2 for y. I get negative 2, sorry. Negative 2 squared is 4, minus 4 adds 0. Now watch this. This is, I'm going to try to use my brain here and say, are there any other ones that are 0? And yeah, whenever you have a 1 and a 1, you'll have a 0. Whenever you have a negative 1 and a 1, or a negative, in fact, everything on this diagonal here is going to be 0. Ditto on this diagonal, because you'll have negative 2 and 2. Oh, that's nice. Notice, not every differential equation is going to be this easy. It's just that this one happens to be nice and easy, right? And it's symmetric both ways, right? Like, I mean, that you plug in a negative x, it's the same thing as plugging in a positive x. So it should be symmetric this way. Ditto with y. But let's just compute these, right? This says x is negative 2, y is positive 1. So negative 2 squared minus positive 1 squared is 4 minus 1 is 3. This we have 0 squared, nope, oop, yeah, see, I messed that up. The x is negative 2 squared minus 0 squared is 4. Now I could use symmetry, but I just want to check myself. We'd have a negative 2 squared minus the y is negative 1 squared is 4 minus 1 is positive 3 again. Yeah? Okay. Here, x is 1, y is 2, so that's 1 minus 4. Negative 3? Yep. Negative 3. Here we have 1 minus 0 is 1. Here, it should be negative 3 again. Let's just check. 1 squared minus 2 squared is 1 minus 4 is minus 3. Okay? And we could just keep going. Everybody sees what I'm doing?
Yeah.
Right? Like if I pointed to one of these, you'd be able to figure it out.
Yeah.
Okay, so I'm not going to go through and do all of these. But it is symmetric. You could use that to your advantage. Though, I don't trust myself to do that. I'll mess that up, obviously. So now, okay, so now we know what the slope looks like at all of those points. And it should, obviously, if we took, go ahead.
It's 4, 1, 0, 2. And the middle one wouldn't be 4, is it? 1, 0.
It should be 1, 4. Oh, that should have been a 2. Let's see, let's make sure. Ooh, no. I messed this up here. This should be a 1. Let's just check. Let's just do it. X is negative 1 squared minus 0 is 1. X is 1 squared minus 0 is still 1. There we go. Okay, that looks good. Yep. Okay. Okay, good. Yes. Okay, so now clearly, just like basically what we're doing now is we're getting linear approximations to this unknown function at all of these different points. And it should be obvious that if we took a finer grid, right, like if we did -2, -1.5, -1, -0.5, 0, and so on. In other words, I made this finer, right? And maybe here also, right? If I made it finer, we would get a better approximation. Right? That should just go without saying, but I'm going to say it anyway. Alright. So now let's do this. Okay, I'm not going to bother putting the numbers in. I'm just going to draw slopes where at these points. So this one here at 0, 0, right, when x is 0 and y is 0, the slope should be 0. So it's just a straight little line like that. Okay, let's fill in as we go this way. We have 1, I move over to 1 and it's a slope of 1. I'm going to draw it a little bit shallower than 1, a little bit lower than 1, because I also have a 4 here and I want that to be pretty steep. But again, you run into trouble if, you know, this is all qualitative, right? I just want, as I look at this, my slope should be increasing. Is my slope increasing as I go that way?
Yes.
Okay, then I feel good about it. And I'm going to try to put that more in the middle here. Okay, ditto that way, right? As we go that way, the slope increases. So we have a 1 and a 4. Trying to make them somewhat even. Now let's go up here. We go up, we're at the origin, we go up 1 and it goes down to -1. So -1 right here. Then up to -4 comes way down like that. Ditto here, we have -1, -4, like that. Okay, now let's do this column here, which is this column. It's at 1, I go up, I get 0, then I go up, I get -3. -3 is not quite this steep, so I'm going to draw him less steep than that. And yes, that looks like -1, Justin. Yes, I know, it's just qualitative, right? We're just trying to get an idea. I just want this one to be less steep than that one, really. The things that are nearby it, that's what I'm trying to do. Okay, this column going down was 0 and then -3. Not quite as steep as that, so I'm going to go like this. Okay, and remember, it's not that the function moves from here to here as it goes by. It's that at this point, if you were to zoom in, it would look like a line like this.
Yeah.
That's what we're trying to convey with this picture here. Okay, over here it's 4, up at 3. Again, those look like the same slope. Again, I don't care. I'm just trying to get a general idea of what's going on. I mean, I should probably make it a little less steep. If that's 4, I'll make it a little less steep. Maybe something like that. Try to do the same thing up here, because that's 3, and then 0. Okay. Over here we have -3, 0, 1, so -3, 0, 1, 0, finally up here to -3. And now this one down here is 0, this one's 3, 4 is steeper, it comes back down to 3, and then goes to 0. Okay, so solution to a differential equation is a function. A particular solution to a differential equation is a function.
Oh, a family.
But and I know. So in general, the general solution to a differential equation is a family of functions. And it depends on where you start, right? And so that's kind of what we're going to do here. What I didn't say is this is problem number 10 from your book. And it says, given this differential equation, what does it say? Actually, I didn't write that down. What does it say to do exactly? It says, it gives you this and says, sketch a direction field for the differential equation. This is your direction field. It doesn't even tell you where to do it. I just chose -2 to 2, -2 to 2. You could do it anywhere, and if they don't tell you, base it at the origin, right? I mean, okay, so that's your default right there. And then it says, then use it to sketch 3 solution curves. So remember, with an initial value problem, you're given something like this, and you're also given where do we start, right? Yeah. And now I could have, and we could do that a bunch of different ways. We could say maybe y of 1 is equal to 2. So that means that this particular solution would go through the point 1, 2. So let's think about that. It goes through the point 1, 2. So let's think about what that would look like if we had this solution curve. Well, right there, it's going to look like a line. So it's going to come down. Then the question is, what does it do? Well, I don't know. I guess basically I'm just going to follow these. Like I'm imagining water pouring through some kind of, I don't know, a bunch of walls, right? It would flow this way, and then I guess, and again, if we had more points here, we could figure out what exactly it's doing. But since I have this grid, I'm just going to assume, okay, it probably comes like that, and then maybe goes like this direction out.
Yeah.
And then on the way back, he's going to go out, but now I don't have any more information, so that's one solution curve right there. The solution to this initial value problem, this guy and that, would look something like this. And if I were really interested in it, I would then go and find more points. I would say, well, what does the slope look like here? What does it look like here? And actually, if I were really interested, I would find what it does here, and what it does here, and what it does here. And that way, I would be able to actually trace out a more accurate thing. But here, I'm just kind of concerned with general solutions here. And we could do this with a bunch of different points, right? And we don't need to do this. I could just say, okay, well, suppose that we had one that started right here at 0, 0. Well, right there, it's going to be flat. Okay, so it's going to be flat, and then it's going to, well, I guess it's going to curve up as it gets closer to here, right? Yeah. Now, notice I'm not drawing a straight line over and then going a straight line here and playing connect the dots like that, because that's not what's happening, right? I have to infer, like, well, I could imagine that this thing, and you could tell, as you move this way, the y value is always 0. The x value is always squared. So he's not going to stay flat for long. He's going to start curving up before he even gets to here, right? Yeah. You know, and that's what we're trying to convey with all of this. And we could just say, okay, well, I guess he would curve up. He would start to curve up, but then up he's gonna hit that guy. So I guess he's gonna flatten out for a while, and then he's gonna hit that guy and then come back up, probably. Moving in the backward direction, I guess he's gonna curve down and then get flat, and then, I don't know, curve down again and do something like that. So that would be another solution curve. Okay. Here's where it's gonna get interesting. So remember, the number 10 said to draw 3 solution curves. So I'm gonna just draw another one. Here we go. Okay, maybe I start over here. It looks like he's going up. So it looks like he's going to go up and then maybe come back down. So, okay, we start here, we go up, and he's going to flatten out and then come back down. And
Can these curves ever touch? This is a pretty hard question. It turns out these curves can never touch. If they touch at a point, because think about how we started with this. I said, give me a point right here. Okay, boom, he goes through right there. Okay, well then, as we move this way, everything's determined by this right here. His entire behavior, his entire motion, is determined by this, right?
Yeah.
Like the derivative tells the function how to move, right? And so if you go through this point right here, then your next bit is entirely determined. Like, in other words, if any function makes it to this point right here, he has to go on this green curve. He has no choice. He can't decide halfway down here, like, I'm going to move off in this direction now.
Yeah.
He's determined by this function. And so, he's determined by this differential equation. And so, if, for instance, this guy did touch here, then they would become the same curve. And it would, even going that way, would
and then even going that way, he would had to have been the same curve. And so, as you're drawing these, take care that they don't ever touch.
I don't think your book talks about this. I was in class with a guy. He's, to this day, the smartest guy I've ever met. We were in a lab together. We were working on something. And we had to draw a few solution curves, this type of thing, right? Based on, we're doing action potentials, so we were monitoring neurons, the firing of neurons. And when a neuron fires, it does this thing like this. If you look at the voltage versus time, there's a quick spike and then it falls off like that. And we're supposed to draw, and there's a differential equation which describes this, and so we're supposed to draw a bunch of curves, right? And like as we were drawing a bunch of these different curves, right? I thought, well, hold up, how do we know that it doesn't like spike up? Like if one spikes up really fast and then comes back down. And he's like, you can't do that. I'm like, well, but how do we know that? He's like, let me show you.
And he just writes this proof. It's just like, suppose that they do touch.
And he basically went through what I just did like here, but like in full rigor. Like
he was a quadruple major. He was majoring in math, neurobiology, chemistry, biochemistry, and then I think he like minored in philosophy or something like that. I think he was the valedictorian or graduating year. Like, yeah, wicked smart guy, and yeah, he was really cool actually. Very, very, very cool. But made me aware of that. Like, oh yeah, no, because if they touch, like it's a differential equation, and so then they have to follow the same trajectory that way. But if they touch, they have to follow the same trajectory in the back way too. Yeah. So when you're drawing these, take care that they don't touch. Otherwise, they're the same curve if they ever do. Does that make sense? Okay. All right. If you increase the resolution, right here, we had 5 by 5 points that we used. If you increase the resolution, you'll get a better approximation. This is, as it stands, not very good, right? But if you increase the resolution, you get better. Okay. Here's another one. So everybody got what we did here? Does it make sense? Because you're going to have to do this. All right? Okay. Okay. Another differential equation. We're going to call this one dy dt. Oops. Blank. Dy dt is equal to 2 minus 3y. This is called an autonomous differential equation. That means that the input variable does not show up in the equation. I mean, you could say it was right there. Well, no, I mean, this is y prime equals 2t minus 3y. That is what we mean by it shows up in the equation. Here, he's not showing up in the equation. It's just y's. I gave away last time how we do the slope field of these guys. It's very simple. But let's suppose that we didn't know that. And what we do is say, okay, well, let's use the exact same grid. I want to find what it's doing between -2 and 2 in both ways. So we have our y here and our x here. X goes -2, -1, 0, 1, 2. And here he goes 2, 1, 0, -1, 2. And now I want to find all of these guys. And so I'm going to start with, how about the left-hand column? And start finding all my answers. Okay. So y is equal to 2 and x is equal, oh sorry, this should be t. Sorry, that should be t. Right? Because it's dy dt. Okay, so we're talking about t versus y because the solution to this differential equation is a family of functions of the form y of t. A particular solution to this differential equation, one of the curves that we're trying to draw, is a function of this form right here. Okay. Now, so we're going to say the slope here at -2, 2 is 2 minus 3 times, I guess the y value is 2, right? So 2 minus 6 is -4. Is that right? Did I do that right? Yeah. Okay. Now we can move over and say, okay, now when t is equal to -1 and y is equal to 2, we have 2 minus 3 times 2, still -4. Right?
Yeah, it's always clear.
And does it change at all? It doesn't change. It's always -4 because t does not show up there because he's autonomous. T doesn't show up. That's what it means to be autonomous. Okay, and so okay, now we move down a column and say okay, when y is equal to 1, we have 2 minus 3 times 1. So that's 2 minus 3 is -1. So we go -1. Then we plug it in again, and we get -1 every single time. We don't need to use our brains anymore, right? We say okay, when it's 0, it's just 2 because I plug in a 0 for y, and I get 2, 2, 2. 2, 2, t didn't matter. Plug in a -1, 2 minus 3 times -1 is 2, plus 3 is 5. I do the same thing when I plug in a -1, and I get a 5. I do the same thing when I plug in a 0, I get a 5. Plug in a 1, I get a 5, and he's still 5. I do this, and I think it's 8. Now, I didn't need to write out all 25. Is it 8?
Yeah.
Because that should be a negative.
Oh.
Ah, yeah. Good eye. Okay, so obviously, if the differential equation is autonomous, you just spent 20. You made 20 calculations that you didn't need to make because you know that in the t direction, it does not change the value that you get for the slope. It's the same every single time. Right?
So, only one solution.
Because it's all, yes, and so, okay, oops. So a better way of dealing with this is the way that I did it last time. Now, let's just keep this, let's just go ahead and do the slope field. Okay, there's this. It's always 2, so when it's 0, it's always 2. So I could say, okay, 2, we're going to make 2 pretty shallow. Why? Because I have a 5 and an 8. So I'm going to make 2 shallow, like this. Okay, when we move up, it's -1. So he's -1 like this. Always, always. When he's up more, he's even more negative. He's -4, like this. Move down here, and it's 5, so he's steeper. Move down here, he's 8, he's even more steep. Okay. Now, a much better way of doing this is when you have an autonomous differential equation. You know that your outputs are going to be that each one of these rows is going to have the same thing. So really all you need to do is find what it is for one row and repeat it over and over and over again. So to find one row, it makes much more sense to just graph this function. My input is y, and my output is dy dt.
So it's just a line.
2 minus 3y is just a line. He goes through 2. Let's do it like this. There's 2. He has a negative slope. Now, anytime we graph, I've been saying this for years, anytime we graph, and your thing goes through an axis, find out where that is. Where is this?
Is there 2?
It's
How do we find...
just 2 equals 2 minus 3.
Hold up. What is the output here?
0.
0.
Yeah.
0. So when the output is 0, we want to know what is the y value.
So it's
So 3y equals 2, y equals 2/3.
Yeah.
Okay, so there, 2/3. So what this tells me then, now you can see how like you could get as many of these as you want, right? Like I happened last time I chose 1, 2, 3, 4, 5 numbers to plug in. Now you could kind of see what's going to happen here. I could say, well, hold up. The output is the slope. The input is the height. Yeah. So when the input y is 0, we're here. This is y equals 0. And we could say, okay, then the slope there is 2. So I draw my 2. And I draw my 2 and draw my 2 and draw my 2 and draw my 2 as many times as I need. Now, when y is bigger than that, we could say he's shallower than that, right? When y is, say, 0.5, he's not as steep, he's more shallow, and so on and so forth. And we get to this interesting point. This is when y equals 2/3. So everybody just kind of remember what we had here. I'm gonna just in general do something like this. What we ended up with was, this was 2, 2, 2, 2, 2. Up here we had negative, negative, negative. He got more negative as we went higher. Here he got steeper, 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 and then very steep as we go down. Okay, so that's what we got via the grid. Yeah? We could do even better with this. And in fact, if I were graphing this, the first thing I would do is say, okay, when the output, when the y value is 2/3, what's the slope there?
0.
The slope is 0 at 2/3. So I'm going to start with my interesting point. The slope is 0 at 2/3. So there's 2/3. When I go bigger than 2/3, when y is bigger than 2/3, then the slope is negative. And the bigger I get, the more negative he gets. So he starts off little negative, gets bigger negative, bigger negative. Yeah? So little negative, bigger negative, bigger negative. Little negative, bigger, bigger, and so on. Bigger, big. Little bigger, big. Little bigger, big. Now it's just the opposite as we go this way. As y gets smaller, then the slope gets more and more positive.
Yeah.
And in fact, we have a value here. But again, this is all qualitative. Like, when I initially did these, I drew this as like a slope of 1/2. It's supposed to be a slope of 2. Doesn't matter. You could just look at this and see, as you go farther down on the y-axis, starting here, you're going down on the y-axis, your slope is getting
bigger. And so you could say, okay, as you get away, he gets more and more and more and more. And then just repeat this, because right, it's autonomous. It doesn't matter what t is doing. Here's my input t. Doesn't matter what t is doing. This picture is going to get repeated all the way over, right?
Yeah.
Like that's what we did at first. And we realized we don't need to do this whole thing. Just find one line and then just repeat that all the way over. Or one column, sorry. Steeper, steeper, steep. Not as steep, steeper, steeper, steep. Not as steep, steeper, and so on and so forth. Not as steep, steeper, steeper, steep. Not as steep, steeper, steeper, steep. Not as steep, steeper, steeper, steep. There we go. Now let's see. We're going to draw, say, 3 solution curves. If we start down here, it's going to shoot way up real quick, but then he's not going to shoot up as quick, and then he's going to stop shooting up as quick, and now he's going to slow down. And now he's going to slow down a lot, and slow down even more. Because, well, that's 0, isn't it?
Yeah.
What about this one? Well, hold up, we'll get there.
So they're all going to approach 0.
It looks like, are they approaching, what value are they approaching?
Oh, well,
2/3.
2/3. But
2/3, okay.
slopes approach.
Right. And so here he's coming down, he's going like that, going like that. Okay, let's do another solution curve. Maybe he starts here, comes up, and he gets less steep and less steep and less steep. And you can't cross the blue one, right?
Yeah.
Right? Anybody over here has to come up higher than the blue and stay higher than the blue forever and ever. Anybody over here has to stay lower than the blue and stay lower forever and ever. So there's your solutions. That's what a solution would look like to one of these guys. Couple questions. What is the limit as t goes to infinity, y of t, if y of t is any solution to this differential equation?
Oh, 2/3.
2/3, very good, very good. And we could infer that from this. In fact, this comes from, I changed the variables up here, but if you're interested in your book, this is an example, and I changed the constants. This comes from Ohm's law, where the, what is inductance? The inductance times the current, the derivative of current, plus the resistance times the current is equal to, is that volts? Yep. Volts. So I just changed the I's for Y's. So Y is the current. And then I plugged in some values which all worked out to give me a 2 and a 3. Right? So if you look at this, this is L dy dt equals E minus Ry. And yeah, I guess you could say if L is equal to 1 and E is equal to, so the voltage is equal to 2 and the resistance is equal to 3, then we could say, well, the current is, we could use this, just this right here. We didn't have to solve the differential equation. We just said, hold up. If Ohm's law says that this is what happens, and the current in this circuit, right, you have an electrical circuit with this setup, like with that much resistance, that much voltage, you have a 2-volt battery on the thing or whatever, then I could tell you what's going to happen to that current as time goes on. That current is going to approach 2/3, what are they, amps. There you go. Okay, so that's the actual example, but I don't care about that stuff. I care about this stuff. This is what's cool to me. So anyway, okay, so there you go. Another question. Let's suppose we had the initial value problem. The initial value problem, which was y prime equals 2 minus 3y
y of 0 equals 2/3. So same differential equation, right? This is what it looks like. What is my solution in that case?
And it's just the line 2/3.
It's just the straight line, right? This thing would be that line right there. He can never move, right?
Yeah.
He can never move because his slope is always 0 right there. It's going to be the constant function, in this case 2/3. And it doesn't matter when that happened either. If he ever became like y of -7 equals 2/3, well, in that case, you would have started here at -7, there at 2/3, and your differential equation would tell that point how to move. It'd say, stay flat, and you move over. Yep, stay flat, move over, stay flat, and ditto all the way back there for infinity. And so, yeah, there we go.
Yeah.
Okay, everybody got that? Okay, now, here we go. So that's qualitatively how you can solve a differential, or how you could get solutions, at least qualitative solutions. I could tell you what's going to happen to a system or something if you have a differential equation where you could get the derivative part by itself. There's another one. Number 24. Gives you, and I've changed the variable names. I want to use f because of what we're going to do here. X times f. Okay, so it's just like the book has y prime equals x minus xy, but I'm going to use y for something else in a minute. And so here's the initial value problem. There's your differential equation, and it says that f of 1 equals 0. So we have some slope field, it does whatever it does. And we have here at 1, you have a 0. And so we have it does whatever it does. I don't care what it looks like actually. There's your thing. What they want us to do, so here's 1. They tell us to estimate f of 1.4. So in other words, here's 1, say here's 2. We want to know 1.4. What is this point here? We want to know when I plug in a 1.4, what is my output? Now, clearly, if I just did something like this, I could estimate this in the following way. I could say, well, hold up now. We know that we're going through here at 1. So let's find the slope at 1. Oh, I'm sorry, 1, 0 is my output, right? Yeah? 1, 0 is my output. So if I know the slope right there, I could do that. I could say, okay, f prime, the slope of the thing, is equal to x is 1, so I have 1 minus 1 times the output 0, 1 minus 0 is 1. So the slope is 1, so I could say, okay, it looks like this. And then at 1.4, we could just use that slope to estimate it. Yeah? Let's see what happens when we do that. If the slope is 1 and that thing's 1.4, I guess we could think about this as a line. Y equals mx plus b. That's why I'm not using a y. That's why I chose to use an f. Okay? We know that the slope is 1. So that's 1x plus b. We also know that here at 1, when I plug in a 1, I get out a 0. That'll help me solve for b. So I'm going to say plug in a 1, get out a 0. Plug in a 1, get out a 0. So then b equals -1. Yeah? And so this approximating line is 1x minus 1. Now I could say, okay then, if that's the approximating line I'm using, I'll just plug in a 1.4. Y at 1.4 minus 1 is 0.4. Done. But
do you think that's going to be very accurate?
No.
Just think about it, right? Like we've done this before, right? You have some function, right? And if you use the first derivative to make a line, okay, it'll work really, really well if you're really close to this function here, right? If you're at 1, then it'll work really well to do, say, I don't know, 1.0001. That's probably good enough to estimate that. But the farther away you go, yikes, life's going to get ugly.
Yeah.
So, think about the way we did this just a minute ago. We took a grid, right? And we said, okay, if we know what it is here, we know what it is here at 1, and I'm trying to get up to 1.4, the more points I have along the way, like if my slope field were the way that I had been doing it, where I'm just using integers, I do it at 1, and then here at 2, and then I do it up here at 1, and then over here at 2. That doesn't tell me what's going on in here, does it? I would like to zoom in and get more points nearby. Yeah? Does that make sense, right? Like if I have a bunch of points here, then I'd have a better picture of what's going on here.
Yeah.
Right? Problem is, I don't want to have to compute like 1,000 of these points when really all I want to do is just find the trajectory of this guy. So, what we're going to do, I want to be able to take this idea of using a slope field, but I want to do it numerically. I don't want to have to draw the entire slope field and stuff like that. But I would like to be able to approximate this thing better. So, okay, remember this is what we got when we used one step to get over.
Yeah.
Okay, another way we could do this is to say we need to get from 1 up to 1.4. And the more steps that we take, I have a feeling that the better the approximation is going to be. And so what I'm going to do is say, all right, first off, let's do it this way. I'm going to kind of go off into general abstract land. Remember, this is the problem that we're working on. But in general, you have some value that you're starting with. We'll call it x0, right? In this case, my x0 is my initial point. So x0 here is equal to 1. Here we're at some x0, just like we've been given. And we have also some y0. I should call it f0. f0, which is, in this case, 0. That's my initial point. In this case, my x0 was 1, and my y0, or f0, my output, my first output, f0, is 0, confusingly. Here I'm not going to draw it that way. I'm going to say whatever that is f0. Yeah? Now what I'm going to do, let's just think about what we did. We took we said, well, we know what the derivative is there, and that gives us some linear approximation. But the farther away I go, I know that it's going to be worse. Unless it just happens to be a good one, right? Like, oh, there's my linear approximation, and my function does this. And then I happen to get it just dead on. We can't count on that, right? Yeah. Usually, everything we've seen, it just gets worse and worse and worse as we go. Okay, so what I'm going to do is take a really small step. Instead of going all the way to 1.4, I'm going to take a small step. And I'm going to call the length of that step h. That's my step size. Okay? Okay. All right, okay. And now what I want to do is try to figure out
what is this next bit? I'm going to call him, that next output is going to be F1 right there. Now just kind of keep it in mind what we're doing here is we have some function. We don't quite know what it looks like. And I'm saying we're going to use the linear approximation for some bit right here, right? Some small step h, right there, to get an approximation of the next point. Once I got that approximation, guess what I'm going to do?
Make it smaller.
Now I'm going to take another step. And the way that I'm going to do this is just keep taking the same size steps. So now that I'm here, I can approximate with this one and find my next approximation of the function. And he's going to be good for a little while. And so that'll work, right? Everybody see what I'm doing here?
Yeah.
And I'll say, okay, he's about like this. Well, what's the derivative there? Well, the derivative there is more like this. Okay, well, I'll take another small step, h. It's not going to be perfect, but the smaller step size that I take, the better it's going to be, right?
Yeah.
Everybody see that?
Yes.
Okay. Is that clear what I'm doing here? Just real quick, I'm going to draw it a little bit better so we could see what I'm doing. We have some unknown function. It does something like this. I'm going to use the derivative of it to find some linear approximation of that function. I'm going to say, okay, there's my x0, and then I'm going to use that with some small step size to get to my next bit, x1. How far away is it? It's h. Now, once I'm there, I could say, hold up, well, we know the input, we know the output. We could plug that in and find the next, or what the derivative is of this function, but now right here. And we'll say, okay, well, we'll use that right here to go and calculate the next step. Again, I move over h right here. I get to x2, plug that in, and I get another approximation. And you can see as I'm doing this, that's better than if I had just plugged it into that first approximation, right? Like it's closer to the original function. Then I go and do it again and say, well, now that I'm here, I'm going to find the derivative of this guy here, which is more like this. And now I'll take another step of the same length. Why do I want it to be the same length? Well, in practice, you might want them to be different lengths. But it's going to make this formula that we're about to derive much easier if they're all the same step size right there. It's much harder. Talk about it in a minute. You kind of see what's happening here? If I'm taking small steps, I can approximate this curve better than if I just used that first derivative and just said, well, what is it right here? Well, it's off by a lot now, right? So that's kind of like what we did here. It was flat, and I used it to go the length of the entire interval. So now what I'm going to do is chop that interval up and get a better approximation by doing this type of thing right here. So that my x0 started at 1 and went up to 1.4. Now, if I do that in one step, it's going to be bad. If I do it in 2 steps, it'll be better. If I do it in 3 steps, it'll be even better. And if I do it in like 100 steps, it's probably pretty darn good. Okay, but let's see. But that's also, I have to do 100 calculations. That seems really hard. It could take a long time. And what you're going to do in the real world is tell a computer to do this for you. In fact, they have solvers. This is what's called a differential equation solver, what we're doing. And there's a bunch of different types. Not all of them use a same step size. Some of them change as you go, and that's interesting. But that's the idea.
What if you let it go to 0?
Well, you don't get anything.
You can't take it in. Wait.
Just a second. Maybe what we're about to do might answer your question. Maybe not. If not, then let's. You could ask again in a second. So let's think about this. we're going from 0 to x1. What I want to do is find what f1 is. Well, this thing right here is a line, y equals mx plus b. Okay. So first, hold it. Let's keep track. We've been given an x0, and we've been given an f0. Now what we're trying to do is find what is f1. Okay? So I've chosen a step size to give me an x1. x1 is just whatever x0 was plus that step size. Yeah? Right? Yeah. That's how we got from here to here. We just add h and we get to our next one. Okay. So the m is what is this. It was the derivative here that I used to calculate this, right? It was the derivative f prime at x0 f0, right? Which in this case would be x0 minus x0 f0, which would be 1 minus 1 times 0, right? That's how we ended up with that right there, right? Everybody remember that? Right? That's how I got that m. I plugged those two values into here, and it gave me a 1. That's why this slope here is 1. Okay, so that's what we did. Okay, but now we're not going to all the way out to 1.4. Now we're just going to x1, whatever that happens to be. So, okay, there's my m. I'm going to replace my m right here with x0 minus, I messed that up, but there you go. I did it in the opposite order. Everybody okay with that?
Yeah.
I just switched the x and the f. Okay, x plus b. Now I know this line right here, when I plug in an x0, I get out an f0. So, y equals, hold up, I'll do it right here. Plug that in. In the first case it turned out to be a 1, whatever. I plug in an x1, oh no, I'm sorry, I plug in an x0, and I get out a f0. Right? Yeah. This is the same thing I did here. The same thing I did to get this. I'm just doing it symbolically now, because I want to figure out a general formula for how to do this method. Okay? So now b is equal to f0 minus this. You know what? I didn't need to. In fact, it's going to be easier on me if I just leave this like this. This particular differential equation has this form here. But I don't care about this particular differential equation, as a matter of fact. I care about this thing in general, because I want a general formula for this. So the slope is just whatever it is when you plug in the value, yeah? The slope is whatever it is when you plug in the value. The slope is whatever it is when you plug in the value. Okay, so the slope is whatever it is, minus that off, equals b. Okay, so I got down to here. Now I'm solving for b by minusing him off over to here. That is what b is. Therefore, my y equals mx plus b is y equals m was f prime evaluated at that initial point, x plus b is this thing. Times x0. Yeah? Yeah. Now what I want, I've already given the output a name. I want, when I plug in an x1, I get out the value I'm trying to find. So I'm going to plug in my x1 now, and that's going to give me my f1, right? When I'll say that again, I have my slope. Plug in my x1, I get out my F1. That's what we're calling F1. Everybody with me so far? All of this right here is just, in general, what I did to get this right here, that particular bit, where I guess the step size was 1.4, or 0.4, sorry, right? H is 0.4 here. Okay, okay, we're almost there. Let's see what F1 is. F1 is equal to, well, hold up. I could put these guys together. I could put my F prime x0, F0, x1 minus F prime x0, F0, x0 plus F0.
Yeah.
Okay, now I'm going to get rid of all of this because that was what we used just to derive. Now I have a formula for my new point. It is nice and general. Okay, it all came from that right there. Now let's see if we could make it even cleaner. I'm going to rewrite this as F0 plus, all right, I'm just bringing the F0 over. I could factor out that, right? I could factor out an F prime x0, F0, like that. What's left is x1 minus x0. What is x1 minus x0? H. It's whatever distance I chose to be my step size. So F1 is equal to F0 plus H times F prime x0, F0. Or in other words, if you run this far, you rise that far. Right? Starting here, starting at F0, how much do you add to get to the next point? Well, H times the slope is how you get that high right there. Yeah. Oh man, that's annoying, isn't it? But I wanted to be 100% sure that when the book said that, they were on it. It is true that all you need to do, if you have a run of this far and you're on a straight line, you just multiply it right there, right? You multiply the distance by the slope and you get the height that you add on. But now that now I'm 100% sure that the book's right about that. Now we have an F1, but we're not done because we're not even close to our final point yet. H is like 0.00000001, and we need to get all the way up to 0.4, right? Because I've chopped this thing into 1,000 little bits right there. Okay, so let's just get a formula for what we do next. So we're trying to get all the way out here to xn, and we're only at x1. So we're going to do the same thing again. We're going to say, well, right here, the function does something else, and the way I find that, I plug it in to find the slope. How do I find the slope? Well, I'm at x1, f1, so I'm just going to plug x1, f1 into this function. So the slope there will be f prime of x1, f1, right? So if we were at, say, 1.01 and 0.2, I would just plug in a 1.01 minus 1.01 times 0.2. And that's what the slope would be there. Okay? And then the way we get to our next point, x2, we're going to take another step, the same type of thing, and we'll just say, okay, well, to get to f2, f2, we start at f1. So f2, how do we get to f2? Well, we start at f1, and then we add h times the derivative at x1, f1, right? Yeah. And I just keep doing the same thing over and over again. Now I recalculate the slope here at this point. It gives me another slope. That slope is given by f prime of x2 f2. Yeah. That's how I get to x3 right here. x3 gets me to f3 and et cetera, or that, yeah. So then the third f would be f2 plus h f prime x2 f2. And I just keep going and going and going until I get to wherever it is that I'm trying to get to. Fn minus 1 plus h times f prime xn minus 1 f n minus 1. Like that. This is called Euler's method. Because, yep, of course Euler figured this out. And so this is how you can approximate. Given some differential equation, you can't find a solution to it. You could just do this. And computers do this very, very well, right? It's obviously like if you have a formula, you could just tell the computer do this and then take those outputs, plug them in. Take those outputs, plug them in. Take those outputs, plug them in. Keep going until you're whatever.
So what if you let n go to infinity?
I think in the limit, like this works out to be like f. Like if you were to do this symbolically, it works out to be f in the limit, right? Like in adding all these up, you end up with some kind of integral of f prime. Yeah, and so that's the idea. Okay, so let's use this to do the thing that we're trying to do. Now here's the thing, it says estimate this. It doesn't want you to use an h of 0.000001. It's going to tell you use a step size of h equals 0.2. Much easier, right? So,
Okay.
yeah, and then it's going to say use a step size of 0.1 as well. But let's just do this. So in
It's a
general,
lot easier than 0.00.
yes, but a computer can do it no problem. A computer can do it in a matter of seconds, not even seconds, like milliseconds. It can do this type of thing. Though there are some differential equations, and I think that it's called if a differential equation is ill-conditioned, this does not work so well. I don't remember there are certain criteria for a differential equation to be well conditioned to this type of problem. So here's my formula. Okay? Now, what I want to do here, because this could get out of hand. I want to keep myself organized here and say, hold up. If I'm using a step size of h is 0.2, then x1 is going to be 0.2 and x2 is going to be 1.4. So that's the last one I want. I want y2, right? Or f2 for this guy. Okay? That's as far as I'm concerned the hardest part of all of this is to keep this stuff straight. So now I've written down my formula and I'm going to say, okay, now let's just plug it in. F1 is equal to, plug in a 0 here. My h size is 0.2. F prime here is, let's find out, F prime, x0 is 1 minus 1 times F0 is 0, so we get a 0. Oh yeah, I remember this. It was 1. Nice. Is that what I got here? Yep. Okay, so F1 is 0.2. Halfway there. Now, we're at the point, so in other words, we started off here at 1, and we used a linear approximation to get us to the point 1.2, and it says that our output there is 0.2. That's what we've just done right here. Now we're going to use that to do the next step, which says that F2 is equal to, you start at the point F1 that you were at, you add your step size times the derivative at that point, at x1 comma f1. F1 we just found was 0.2. H is also 0.2. F prime at x1 f1. Now here's where it's going to get ugly. Yeah, we're just going to plug it in. So f prime x1 is 1.2. See, isn't it nice that I wrote that down ahead of time?
Yeah.
Because if I just asked you, wait, what's x1? I forgot already. I went ahead and did the work. Okay, so I could just look and go, ah, that is 1.2. I don't need to worry about it. f1 is 0.2. So 1.2 minus 1.2 times 0.2. I worked this out and got 0.96. So this is 0.96. 0.2 plus 0.192 is 0.392. And F2 was the bit that I was looking for, right? That's 1.4. So we got 0.392. So initially with our 1 we had 0.3, sorry, we had 0.4. This was when our step size was the whole thing, 0.4.
Yeah.
Now we just got that it's 0.392, and that was when the step size was 0.2. Number 24 says first to do it with a step size of h equals 0.2, then do it again with a step size of h equals 0.1. So I want to finish this up and actually work this one out. So if h equals 0.1, our initial conditions are the same because it was given right there. This is that. X0 is the initial input, F0 is the initial output. And so now we're given a step size. So we start at X0 is 1, add 0.1 to that, you get 0.1. Then X2 is 1.2. X3 is 1.3. X4 is our stopping point. It's also nice to do this so you know when to stop, right? I can just look at that and go, yep, that's the input I want. So I'm looking for F4. So F0 is given, so now we do F1, which is F0 plus H F prime of X0 F0. I will spare you all of the plugging stuffs in and whatnot, okay? So we get F1 is 0 plus 0.1 times, plug it in, and this thing, of course, was still 1. So now we have 0.1 for F1.
Yeah.
Now, F2 is F1 plus H times F prime at X1 F1. Plug in X1, I'll just do the whole thing. F1 we just found was 0.1. H is given 0.1. F prime at this, when you plug it in, you get 1.1 minus 1.1 times 0.1. This works out to 0.1 plus 0.1 times 0.99, which is 0.1 plus 0.099, which is 0.199. So that's F2. Halfway there. F3 is F2 plus H times F prime of X2 F2. F2 0.199 plus H is not changed. Plug X2, which is that, and F2, which is that, into that, and you get 1
1.2 minus 1.2 times 0.199. That works out to 0.19 plus 0.1 times 0.9612, which is 0.199 plus 0.09612, which is 0.29512. You will want to use a calculator for these.
Yeah.
Super easy, and you can't do it for this homework, but if you know Python, or really any programming language, of course, but in particular Python, it's so easy. You can probably figure out how to do this. Now, the next one comes from the previous one, f3. H f prime at x3 f3. And so f3 was this 0.29512 plus h has not changed. This works out to be, when I plug in an x3, I get 1.3 minus 1.3 times this stuff, 0.29512. Long story short, that works out to 0.3867544, and that is the bit that we were looking for. Because x4 was the stopping point that we're looking for, and so now we've estimated it to be 0.38, we'll call it 68, when h was equal to 0.1. And you could bet, you can see what's happening, right?
Yeah.
Like, and it kind of makes sense intuitively with what, or with the picture that I initially drew here. Is like, we're starting here, we have some function, and I'm guessing it's probably doing something like this, because our initial thing was an overshot, right?
Yeah.
When we're trying to figure out what it is here at x equals 1.4, we use our initial one, which is what we did there. We use that one, h equals 0.4. That's the entire step. We did one step, and it overshot it by some amount. Then we said, okay, when h is equal to 0.2, we took 2 steps. There's 0.2 right there. And we got, okay, there was my, right here. And then I used the tangent line here to compute this guy right there, right? That's how we got, so that top one was an output of 0.4. Our second one was 0.392. And then we used step sizes of 0.1. 0.1 from here to here. 0.1 from here to here. 0.1 from there to there, and another 0.1 from there to there, and let's see what happened. We used the same bit to get to here, then we used the tangent line from here to here to get to here, then we used the tangent line from here to here to get to here, then we used the tangent line from there to there to get to here, which was our next approximation, 0.3868-ish, to get that. And you can see how the smaller you make h, the better your approximation is going to be. I think you have 1 or 2 problems that say to draw a bunch of solution curves like this as well, or draw the approximating things as h increases, if that makes sense what you're doing here. Did all of this make any questions about any of this? Did your question get answered that you were saying?
Yeah.
Okay. Okay. One thing I do want to say, if you just plug this in, actually, and use y. The only reason I used f is because I wanted to use y equals mx plus b, and I didn't want us to confuse the line y equals mx plus b for the actual function that we're looking for.
which is what this would have been if I did this. You know what I'm saying? If all of these were y's, then we have a linear, then we have another y equals mx plus b, but this line is not the same y, right? So, but what you're going to see in your homework is they're all y's, okay? There's never f's, or they might give you, I don't think they do, I think it's all, they always use y's here. That's what's going on here. One final thing, if you plug this into Wolfram Alpha, it will give you a slope field. How cool is that, right? Like any of these that you have, you can just scroll down and see the slope field.
Yeah.
That's cool. I want to say one more thing. Numbers 3, 4, 5, and 6. You're only doing 3 and 5. They give you, for instance, y prime equals, this is number 4, x 2 minus y. And all of them, 3, 4, 5, and 6, says to match the given thing with the slope field that they've drawn. Now, you could just sit there and look at that and look and look and look and look. I think it's better for you if you just forget about the picture for a second. Just draw this one out. Like, you go find a slope field for this guy. Just draw him out real quick. And then look and say, and then when you look and see, hey, that one looks like the one that I did, you feel good because you actually solved a problem. You weren't just looking and using process of elimination to try to say, well, that one can't be that one. This one's definitely that one. So this one's probably either this one or this one. You just, like, you'll feel much better about yourself if you draw out a slope field and then you look and you see that slope field that you just drew and you go, yeah, I did good. Like, okay? Yeah. Although, anyway, that's all I'm going to say. Any questions?
Are all the slope fields that they have in there, they're like exactly accurate, right?
Yeah. They're all computer generated, and so yeah. And the one, like, if you get one from Wolfram Alpha, it'll be, you know, computer generated, so it'll be good. Yours do not need to be. And as we saw, we were able to see, like, the long-term behavior of a differential equation just by going, well, it's like 0 here, and those are negative, and these are positive, and so it's gonna go to 0. It's gonna go to like 2/3. Yeah, it's actually really useful, especially when you have systems of differential equations.